Let's crank this up. No soft intros, no gentle guides, just raw, unfiltered reality smashing. There's an apple on your desk. So what? You think you know what it is? You think it's just a piece of fruit? You have no idea. Flip on your supernatural vision, yes, that God-tier zoom lens, and stare it down. First level, boom. Every wrinkle, every pore on the skin of that apple leaps out like craters on Mars. Crank it higher, 100 times. Now you're drowning in a sea of plant cells, millions of microscopic chambers pulsing with life. You've already lost sight of the apple. That thing is gone. It was never real to begin with. Keep going. The cells collapse. You're diving through tangled chains of carbon, hydrogen, oxygen molecules, dancing like drunks at a subatomic rave. But you're relentless. You push deeper, and suddenly the apple explodes into 10 octillion atoms. 10 to the 27th. That's not fruit. That's a galaxy of madness. Grab an atom, zoom. Electron cloud, nothingness. But hold up. Dead center? A speck, an atomic nucleus, smaller than anything you've ever imagined. You think you've hit bottom? Nope. Crack open the nucleus, and now you're inside protons and neutrons. They shatter into quarks and gluons, tiny goblins of chaos flipping you off as they glitz in and out of existence. This isn't physics anymore. This is quantum anarchy. Probabilities rule here. The apple? It's not matter. It's not even energy. It's a freaking vibration across quantum fields. But guess what? Some physicists say this rabbit hole goes even deeper. Go further, and those quarks might dissolve into pure data. Qubits, logic gates of reality itself. Bits of information, existing in multiple states at once, tied together across time, space, and whatever else is hiding behind the curtains. Space and time, optional settings. Maybe we're just background code running in some alien's graphics card. Maybe this whole universe is a beautifully rendered lie, a hologram, or worse, an equation. So ask yourself, what is real? You can bite the apple, smell it, taste it, feel the waxy skin, but all you're sensing is a story your brain tells itself, a dumbed-down version of the truth so you don't lose your mind. Reality? It's not what you think. It never was. Our ancestors thought the world was solid, obvious, simple. They trusted their senses. The rustle in the bushes meant food or a predator. Back in the day, reality was life or death. But then the human brain started doing something insane. It started thinking, not just reacting. Suddenly we weren't just animals running on instincts. We were creatures haunted by meaning. And death? We didn't just accept it. We buried our dead. That means we thought about what happens next. We created gods, spirits, heavens, hells, because we couldn't stand the idea that there wasn't something more. Then Plato came along and dropped a philosophical nuke. According to Plato, our world is unreal. His cave allegory slaps harder than most sci-fi. Imagine people chained in a cave staring at shadows on a wall their entire lives. That's us, says Plato. We're looking at shadows and calling it truth. Meanwhile, reality is blazing behind us, and we can't even turn our heads to see it. Fast forward to modern science, and guess what? Plato's not looking so crazy. Let's talk about color. You look at a green apple and say, yep, that's green. But where the hell is that green actually located? It's not in the apple, it's in your brain. Thomas Young was the first to notice the connection between vision and color. He suggested that our eye contains 3 kinds of fibers, what we now call cones. One kind is sensitive to red, another to green, and a third to blue. That's it. Your brain blends the signals and paints the illusion of color in your mind. And that illusion, it's not even universal. Monkeys see the world sort of like us. Most mammals? Worse. They only have 2 color detectors. Their world is duller, flatter. Insects, totally different league. Bees see ultraviolet, the psychedelic paint splashes on flowers that we can't even imagine. Birds, reptiles, and fish, many of them have 4, 5, even 6 kinds of color receptors. They're seeing colors that don't even exist for us. But the real MVP of vision? The mantis shrimp. This monster doesn't have 4 or 5 photoreceptors, it has 12. That's not vision, that's a sensory rave we'll never be invited to. What do we do with all these wildly different versions of reality? For you, yellow is the color of a banana, but to another species, that same banana might scream strawberry red, or broccoli green, or maybe even the exact shade of your skin. Your true colors aren't truth at all. They're just your brain's best guess. Reality? It's filtered, fabricated, and force-fed through the squishy gray simulator in your skull. Sound? Same deal, just pressure waves jiggling your eardrums. Your brain spins those wiggles into voices, music, birdsong. You're not hearing the world. You're hearing your version of the world. You think you live in reality? No, you live in a hallucination. A highly convincing, meticulously constructed, brain-generated virtual reality. But here's the twist. That apple you're holding, the one you swear is real, solid, safe, science took a hard look under the hood and found something disturbing. They found nothing. Zoom in far enough, and that apple turns into a cloud of probabilities. The closer you get to the core of matter, the less matter you find. Solidness is an illusion. The entire universe is built on ghost particles and mathematical whispers. And that's not even the wild part. Let's talk size. The cosmos isn't just big, it's insanely big. You think your apartment is small? Blaise Pascal, one of the sharpest minds of his time, once said the universe made him feel like a speck of snot. Yep, snot, floating in an infinite abyss. But instead of curling up and crying about it, people got obsessed. They started measuring the abyss. Euclid gave us the rules. Basic geometry, triangles, straight lines, all the clean stuff. And for a while that worked great. Gauss even climbed mountains to test it out, and sure enough, the math held. Fast forward to now, your GPS wouldn't even work without old Euclid doing his thing. But then, we leveled up. We pushed past Earth, past comfort, past Euclid. Out in deep space, all that simple geometry starts to break down. Parallel lines, they curve. Triangles, their angles lie. Euclid's tidy world collapses under the weight of cosmic scale. So we pulled out the big guns. Gamma-ray telescopes, neutrino detectors, gravitational wave catchers. We built instruments that see the invisible and measure the immeasurable. With their help, scientists have made 3 important discoveries. First, matter is the same everywhere. It doesn't give a damn where it is. The hydrogen in your tap water is the same as the hydrogen tearing through a quasar 10 billion light-years away. Physics doesn't play favorites. The same laws are laying down the rules from here to the edge of the observable universe. Second, the universe is a cosmic nesting doll. Stars get packed into galaxies, galaxies into clusters, clusters into superclusters, and almost every star, like our mediocre sun, is babysitting a pack of planets. We've found thousands, we're just scratching the surface. Third, the cosmos is weirdly even. No matter where you look, galaxies are spaced out like someone with OCD designed it. Same density, same patterns, stretched across billions of light years. Now, let's talk about how the hell we know any of this. Nobody's joyriding to the edge of the universe with a ruler. Astronomers play it smarter. They let light do the legwork. On Earth, light sprints around the 6,400-kilometer radius in about 0.02 seconds. Easy. The Sun, light takes 8 minutes to reach us. Proxima Centauri, 4 years. And we're just getting started. For the big leagues, astronomers use standard candles, objects that always shine with the same brightness. If one looks dimmer, it's farther away, like a flashlight across a parking lot. Cepheids, pulsing stars with rhythms tied to their brightness, are the universe's Morse code. Henrietta Leavitt cracked the pattern, and suddenly, boom, we could measure distances to galaxies. That's how we mapped the Milky Way, a gigantic spinning disk about 100,000 light-years wide, thick in the middle, thin on the edges. Between galaxies? Gaps, hundreds of thousands of light-years wide. But then comes Edwin Hubble, the man who rewrote the universe. He realized that galaxies aren't just sitting still, they're fleeing, and the farther they are, the faster they're running. The light they emit, stretched to the red side of the spectrum, Doppler effect on a cosmic scale. Translation, the universe is expanding, space itself is growing. Now hit rewind, galaxies rush backward, closing in. The whole mess contracts to a single point, about 13.8 billion years ago. The moment of the Big Bang, or as Georges Lemaitre called it, the cosmic egg. That's not poetry, that's physics. And here's the kicker. When we peer deep into space, we're staring into the past, because light has a speed limit. The farther you look, the older the image. You're not seeing galaxies, you're seeing their ghost light, broadcast billions of years ago. The oldest light in the universe? It's been traveling for 13.8 billion years just to hit your eyeballs. That's the cosmic microwave background radiation that finally broke free when matter stopped choking it out, around 380,000 years after the Big Bang. Every second, the edge of our universe pushes further outward. And while a day doesn't mean jack in cosmic terms, it begs the question, what the hell are our descendants going to see billions of years from now? What's waiting beyond the visible universe? Maybe the whole damn thing. If it's finite, we'll see all of it eventually. But don't confuse finite with limited. Just like a globe doesn't have an edge, our universe might be a three-dimensional loop. No wall, no border, just infinite curvature. Everywhere we look, it's the same song, same hydrogen, same galaxies, same physics. But what if just beyond our cosmic curtain, everything's different? What if we're just a speck in some wild multiverse where the laws of nature flip the bird to ours? You want to find out? Then point every telescope, satellite, and quantum eyeball toward the edge and look for something weird. Let's rewind a bit. Newton thought gravity was like some spooky invisible hand pulling planets across a void instantaneously. Sounded like magic. Then came Michael Faraday, a dirt-poor tinkerer with no formal education who dared to say, hey, maybe space isn't empty. Maybe it's a web of invisible force lines. He called them fields. Enter James Clerk Maxwell, a stone-cold math genius. He took Faraday's hand-wavy ideas and turned them into equations that cracked the universe. He found that electric and magnetic fields can loop into self-sustaining waves that travel at, you guessed it, the speed of light. And light? Light is that wave, but that's not all. Maxwell's math said there were waves we can't even see. A couple decades later, Heinrich Hertz built a damn radio using that prediction. Now we know the entire electromagnetic family. Radio waves, X-rays, gamma rays, the whole invisible zoo. Then the 20th century rolled in, and Einstein had to mess with everything again. He said, hey, light's also made of particles, photons. Great. So is light a wave or a particle? Answer, both. Deal with it. Quantum mechanics entered the chaps and said everything's just a ripple in a field. You're a bunch of quantum vibrations. An electron? A blip in the electron field. Quarks? Waves in the quark field. That's why every electron in the universe is identical. They're not individual things. They're manifestations of the same cosmic source. And Frank Wilczek, Nobel Prize-winning badass, puts it perfectly. From forces, we go from forces to fields, and from quantum fields to particles. From particles, we go to quantum fields, and from fields to forces. In this way, we realize that matter and force are two aspects of a single, underlying reality. This is where physics got flipped on its head. Fields weren't just some nerdy math trick anymore, they became the language of the universe. You want to know what a particle is? It's just a twitch, a ripple in some invisible quantum field that stretches across all of space. And forces? Same deal. Matter and energy. Turns out they're just different dance moves of the same cosmic field. Now let's talk about that tiny, elegant monster of a formula, E equals mc squared. Seen it a million times, but you probably haven't felt what it means. Flip it around, m equals E/c squared, and suddenly, mass isn't some ancient, sacred property. It's energy. That's it. Energy tied up in a knot so tight it becomes weight. Inside every proton in your body, quarks and gluons are racing around like maniacs. The quarks barely weigh anything. The gluons? Weightless. But their motion, their raw, relentless energy is what makes up nearly all the mass of you. You're not solid. You're a storm of energy, held in place by math. And Newton, for all his genius, was scratching his powdered wig over something weird. Everything falls at the same rate. Doesn't matter if it's a bowling ball or a feather in a vacuum, they drop like twins. Why? Newton didn't know. His laws had two kinds of mass, one for inertia, one for gravity, and by some cosmic fluke they were always equal. It worked, but it made zero sense. Then Einstein kicked down the door in 1915 and rewrote reality. Gravity, not a force. It's the warping of space-time itself. Heavy stuff like the Earth or the Sun don't pull you. They bend the fabric of existence around them. You're not being yanked down, you're sliding along a warped landscape. Every object, no matter what it's made of, just follows the same twisted geometry. You're not falling, you're gliding on curves you can't even see. And that's why everything falls the same way. Not because of mass, but because space-time is telling you how to move. That's the game. That's the truth. Space-time tells matter how to move. Matter tells space-time how to curve. John Wheeler. Here's what's truly insane. Gravity isn't just about mass, it's about energy. Any energy. Even light, which has no rest mass at all, can warp the very fabric of space-time. That's not a poetic metaphor, that's physics. Einstein didn't just give us some fancy math with E equals mc squared, he gave us a map of the universe where everything is energy, and that energy bends reality itself. Space-time isn't a stage we act on, it's the dance floor being twisted by every move we make. And that's just the big picture. Dive into the atomic world and things get even weirder. We started with basic tools, glass lenses, optical microscopes, great for peeking at cells and bacteria, but try zooming in past the wavelength of light and suddenly, boom, clarity collapses. So what did scientists do? They hacked the problem. Enter X-ray diffraction, where you blast X-rays at crystals and decode how the rays scatter like encrypted alien signals. That's how we cracked table salt, then cholesterol, then penicillin, then the Holy Grail, DNA. The double helix was just a scrambled echo, unraveled by brains sharp enough to see patterns in the chaos. Still not enough resolution? No problem. Enter the scanning microscope, a tool that doesn't see, it feels. Picture a needle so sharp it makes a razor look like a brick. You drag it across a surface atom by atom, like reading Braille written in quantum bumps. The closer it gets, the stronger the electric current. And what do you see? Atoms, literal atoms, not theories. Mountains on the atomic landscape. But none of this compares to what happened in 1913. Geiger and Marsden under Rutherford fired alpha particles at gold foil, expecting them to pass through like ghosts. But some particles bounced back, hard, like a cannonball ricocheting off tissue paper. It shattered the model of the atom in one shot. Almost all the mass was crammed into a tiny, invisible nucleus. Picture this, if the atom were the size of a soccer stadium, the nucleus would be a grain of sand, and everything else, empty space. That experiment cracked open the subatomic vault. Since then, we've been smashing particles harder, faster, deeper, like intellectual wrecking balls, ripping apart matter to see what's hiding inside. And if there's one truth, one sacred mantra that deserves to be etched into the memory of civilization, it's what Richard Feynman said. If all scientific knowledge were to disappear and only one phrase could be handed down to posterity, I would choose, everything is made up of atoms. The word atom sounds ancient, and it is. It comes from Greek meaning indivisible. Cute idea. For centuries, scientists bought that story. Atoms were the smallest unbreakable bits of matter. Spoiler, they were wrong. Because atoms, they're mostly nothing. Inside them, electrons zipping around a nucleus so small it takes up 1/1000th of a millionth of the atom's volume. That's like hiding a grain of sand inside a cathedral and calling it full. And just like that, the grand circle closes. The same insane structure patterns the cosmos above and the particles below. So how the hell does this quantum zoo operate? Physicist Frank Wilczek lays it down with 4 ruthless rules. The universe is in motion. Laws describe change, not stillness. These laws are universal, no exceptions, no backstage VIP passes. They're local. The future of anything depends only on what's nearby, and they're precise. Clean-cut equations, no improv. Now, let's rewind all the way back to a time when philosophers didn't have TikTok. Democritus, Greek legend, looked at the world and said, "You think you see color, sweetness, bitterness? Nonsense. All there is are atoms and the void." Of course, he imagined them as little metal Lego blocks with hooks. Turns out, nature's toolkit is even simpler and crazier. Modern physics says everything that exists has only 3 core traits: mass, charge, and spin. That's it. You could fit the blueprint of the universe on a post-it note. Spin? Not like your washing machine. We're talking about an eternal quantum pirouette that makes no sense to the human brain. No wobble, no edges, just math doing ballet in the void. And here's the kicker. These particles don't even have a physical size. They're points, just math floating in space. All of reality, your dog, the sun, your brain, your ex's bad taste in music, is built from 5 tiny particles. 5. The whole circus. The story kicked off in 1897 with J.J. Thomson, who was basically playing with lightning in a glass tube and accidentally discovered the electron. Then came Einstein, the rock star of 1905. He said, "Hey, what if light isn't just a wave, it's made of particles?" Everyone gasped. Even Max Planck, the godfather of quantum theory, was like, "Yikes, tone it down." But guess what? Einstein was right again. The photon was real, and it won him a Nobel. Zoom into the atom, and here's what you find. Electrons are glued to a nucleus by the electric force which rides on, you guessed it, photons. Inside that nucleus, protons and neutrons. Inside those, quarks, specifically 2 kinds, up and down. And they're held together by badass force carriers called gluons. Think of them as quantum duct tape with attitude. Let's talk about the graviton, the phantom particle that supposedly carries gravity, the very force that glues stars, galaxies, and the entire damn universe together. Have we ever seen one? Hell no. It interacts with matter so weakly it might as well be a ghost. But don't let that fool you. Trillions of these invisible bad boys together create the force that literally shapes the cosmos. And with that, here's the mic drop. Every apple, every planet, every black hole, everything is made of just 5 particles. Electrons, photons, quarks, gluons, gravitons. That's it. Each one comes with just 3 core properties: mass, charge, and spin. That's all it takes to build everything from Mozart's brain to your breakfast burrito. Ultimate simplicity, infinite variety. Now, buckle up, because the whole universe runs on just 4 fundamental forces. Think of them as the 4 horsemen of physical reality. Electromagnetism. This one's your daily driver. It holds atoms together, paints the sky, powers your phone, and gives you the thrill of a lightning storm. The strong force doesn't mess around. It's the nuclear superglue that keeps protons and neutrons from flying apart like an angry divorce. Without it, atoms would just explode. Gravity, usually chill, barely noticeable between atoms, but get enough mass together and gravity becomes the boss. It holds galaxies together, bends space, and makes black holes inevitable. The weak force. It's the cosmic whisperer, causing radioactive decay and making the sun shine. Without it, you'd be sitting in the dark, wondering why you're cold and dead. And here's the kicker. All 4 of these universe-defining forces can be boiled down into a few short equations. The entire operating system of the cosmos is simpler than the code on your smartphone, and a hell of a lot more elegant. But get this, we didn't figure this out in some abstract void. Scientists tested these laws in the real world, then zoomed in and asked, do they hold up inside atoms too? Turns out yes, and it's glorious. The same rules apply all the way down. Atoms, when struck by light, sing. They hum their own unique tune by absorbing and emitting light in quantized bursts, fingerprints made of photons. We call it a spectrum, and it's how we know what stars are made of, even if they're light years away. In 1913, a young physicist named Niels Bohr cracked the code for hydrogen's glow. He worked out exactly which colors it could emit. Einstein heard about it and couldn't believe his ears. He called it the highest musicality in the realm of thought. The essence of the structure of matter is music. There was no logical reason to expect that the mathematics developed to understand music should have anything in common with atomic physics. Yet it turns out that the same concepts and equations govern both realms. Atoms are musical instruments, and the light they emit makes their sound visible. Frank Wilczek. Back in 1929, the legendary physicist Paul Dirac dropped a bombshell. We already know all the fundamental laws of physics and chemistry. People scoffed. Arrogant, maybe, premature, possibly. But nearly a century later, guess what? He wasn't far off. We've built lasers that slice through steel like butter. We've made GPS systems that tell you where you are to within a meter using equations from Einstein. We've got transistors so small they dance on the edge of quantum weirdness. Nuclear reactors, MRI machines, satellites, all ticking along like clockwork, powered by the same laws Dirac was talking about. 4 forces. That's it. That's the skeleton key to the universe. Gravity, electromagnetism, the strong force, the weak force. Together, they form the rock-solid foundation of modern physics, the bedrock of our reality. The general theory of relativity teaches us that the division of space-time into space and time is unnatural. The cosmological theory of the Big Bang says that the early universe was remarkably simple. These facts are a clear hint that we should look for more comprehensive laws that allow us to see the world as a whole. Frank Wilczek. What if everything we know about the universe is just off? What if time doesn't flow and reality doesn't happen, but just is? That's exactly what mathematician Hermann Weyl dared to say. The objective world just is. It doesn't happen. Let that sink in. In 1935, Einstein tried to expose quantum mechanics as nonsense. He cooked up a mind-bending experiment. 2 particles shoot out from a single point in space, spinning in perfect opposition. One goes up, the other down. Yin and yang, locked in cosmic choreography. Now stretch them light years apart. According to quantum theory, neither particle has a defined spin until you look, until you measure. And the second you observe the spin of one, bam, you instantly know the spin of the other. Einstein flipped. How is this possible? He demanded. Information moving faster than light? That's sacrilege in physics. So he clung to hidden variables, little ghosts inside particles secretly predetermining their fate. But then came John Bell in the 1960s. He built a trap, a test, a way to force the universe to come clean. And the results? Devastating. There are no hidden variables. Spooky action at a distance is real. Touch one particle, and the universe knows instantly. In 2022, they handed out a Nobel Prize just for proving how weird reality really is. And here's the kicker. Nothing in this universe stands alone. Every atom, every particle, every apple on your desk is plugged into the whole damn cosmic mainframe. You're not separate. You're a node in the network, a ripple in the quantum web. Einstein never made peace with it. On his deathbed, he didn't ask for family. He asked for 3 things: his glasses, his pen, his equations. Because even in his final breath, he was chasing the same dragon, the theory of everything, the one code to unify all the forces of nature, and we're still chasing it today. Modern physics is built on 2 titans: Einstein's theory of relativity and quantum mechanics. One turns gravity into warped space-time. The other treats reality like a probability game played by invisible waves and particles. Both are genius. Both are flawless in their own arenas, and yet they refuse to shake hands. Relativity speaks the language of smooth geometric elegance. Quantum mechanics? It's pure chaos full of twitchy electrons, jumping particles, and bizarre entanglements. Try throwing them into the same room, and the equations start screaming. So how do we make sense of this mess? Let's start with the quantum world. Every particle? It's just a ripple in a field. Electrons ripple in the electron field. Photons in the electromagnetic field. Quarks? They're trading gluons, like Wall Street brokers with anger issues. A neutron decays because one of its quarks flips into another via a W boson. A twitch in the weak field that lives and dies in a billionth of a second. The result? A proton, an electron, and a neutrino. Quantum mechanics nails it all, except gravity. Physicists have tried everything, turned particles into vibrating strings, quantized space-time itself, bend math around 11 dimensions. Still, no unified theory, no ultimate answer. But there's one word that might crack the code: symmetry. Not just pretty patterns, real symmetry. The kind that dictates which particles can morph, what reactions are possible, and what the universe is allowed to do. Every symmetry ties to a fundamental law. Time symmetry gives you energy conservation. Spatial symmetry gives you momentum. This isn't decoration, this is law. And physicists are betting that if we can find the deepest symmetry of them all, we'll finally stitch everything, gravity, quantum mechanics, all of it, into one seamless equation. Einstein died chasing that dream. But it's not dead. In fact, things got weird, in the best possible way. In the late 90s, a physicist named Juan Maldacena made a move no one saw coming. He found that a universe with no gravity in 4 dimensions is mathematically identical to one with gravity in 5. Think about that. 2 totally different realities, one without gravity, the other with, are just alternate forms of the same fundamental truth. It's like finding out your 2D sketch is secretly a 3D sculpture, and you can flip between them at will. Maldacena's discovery didn't just mess with our heads, it shook the foundations. It meant that to truly understand the nuclear forces inside our 3-dimensional world, we might need to take a detour into 5-dimensional gravity. This caused quite a stir in the physics world. By 2015, 10,000 papers had been published in which authors cited Maldacena's work, making it the most influential paper in high-energy physics. Michio Kaku. This research led to the discovery of the holographic principle. Just as an ordinary hologram stores a 3-dimensional image on a flat sheet of paper, our universe may be like a giant hologram. Maybe we are like shadows of more complex beings, living in a world with more dimensions. When we walk down the street, our shadow follows us and moves like us, except that it exists in 2 dimensions. Similarly, we ourselves may imagine shadows moving in 3 dimensions, but our real selves are moving in 10 or 11 dimensions. Michio Kaku. What if everything you see, touch, feel, your body, the sky, the stars, is just a cosmic illusion? What if reality as you know it is nothing more than a projection from another dimension? Yeah, a hologram. It sounds insane, right? But that's exactly what some of the brightest minds in physics are telling us. As Jacob Bekenstein once put it, a grain of sand may not contain our world, but a flat screen might. Wrap your head around that. A flat screen might hold the entire universe. And Raphael Bousseau? He doubled down. The world doesn't look like a hologram to us, but in terms of information, it absolutely is. And the crazy part? It works everywhere, in all versions of space-time, and we don't know why. Well, this isn't science fiction. This came from the study of one of the universe's strangest monsters, black holes. You'd think black holes are complicated. They're not. They're ridiculously simple. All you need to describe one is mass, spin, and charge. And charge? It's so small it barely matters. So really just mass and spin. That's it. Now throw a book into a black hole. What happens? The words, the story, the paper, it all vanishes. Poof, gone. And that's a problem, because physics has a rule. Information can't disappear. Ever. It has to go somewhere. Then came Hawking. He showed black holes aren't completely black. They leak, slowly, quietly. They emit radiation and evaporate. But wait, if they're leaking energy and shrinking, where does the information go? And to the wild idea, maybe the information never falls in. Maybe it sticks to the surface, the event horizon, like a tattoo made of pure data. Maybe black holes are nature's ultimate hard drives. And here's the twist that'll fry your circuits. If this works for black holes, what if everything works this way? What if the universe, this giant 3D arena we call home, is actually a projection from a 2D surface way out on the cosmic edge? What if we're just living inside a holographic playback? Space, time, matter, maybe none of it is as real as it looks. Maybe we're shadows cast by something deeper, something far stranger. The entire universe is a giant holographic memory that is increasingly filled with data over time. This filling of cosmic memory is what we think of as gravity. If the memory fills up completely, you end up in a black hole. Eric Verlint. Theoretical results suggest that our universe, which we perceive as 3-dimensional, may actually be recorded on a two-dimensional surface, like a hologram. Our everyday sense of the three-dimensionality of the world would then turn out to be either a profound illusion or just one of two alternative ways of looking at reality. Jacob Bekenstein. I'm holding an apple, I can feel it, see it, but let's be real, I have no idea what it actually is. Whatever the hell is going on at the quantum level, at the edge of a black hole, wherever, but there is one thing I know for sure. The damn thing exists. Right now, and maybe that's the key, not some spooky math or abstract particle, the now, the moment, time. But what even is time? St. Augustine said it best, if no one asks me, I know what it is, but if someone asks, I'm lost. That's not just poetic, that's the truth smacking us in the face. We use time every day. We measure it, chase it, run out of it, but try to define it? Good luck. Here's the simplest take. Time is the one thing keeping everything from happening all at once. Nature runs on rhythms. The sun rises, the moon cycles, seasons march in step like soldiers on parade. Our ancestors locked in on that cosmic drumbeat. They tracked the sky, invented calendars, planted crops, predicted migrations. Survival ran on time. Now we've pushed the envelope. We've built clocks that don't tick, they decay. Carbon-14, it's the universe's forensic tool. Living things soak it in. When they die, it starts disappearing. 5,730 years later, half of it's gone. So we measure what's left and boom, we date fossils, bones, cave paintings. That's how we know Neanderthals vanished 40,000 years ago, and we, Homo sapiens, showed up just 300,000 years back. That's 10,000 generations. A blink. Want a longer view? Look up. Star clocks. Our sun is a ticking time bomb. In 5 billion years, it'll puff up like a balloon, swallow Mercury and Venus, then collapse into a white-hot Earth-sized ghost. That's not theory. We've seen it in other stars. We know how the cosmic clock ticks. And guess what? If you compress the entire 13.8 billion-year history of the universe into 1 year, humans would show up in the final 40 minutes of December 31st. We're not late to the party. We're practically still at the door. For centuries, everyone thought time was steady. Then Einstein showed up and said, nah, time's a lie. In 1905, he dropped a bomb. Time is relative. Imagine twins. One stays on Earth, the other rides a rocket near the speed of light. When they reunite, the astronaut's younger. Why? Because motion bends time. And this isn't sci-fi, it's measured, it's proven. Muons, tiny particles born in the upper atmosphere, live just 2/millionths of a second. They should die before hitting the ground, but they don't. Why? Because at high speeds, time slows down. For them, it stretches. Then came 1915, Einstein's general theory of relativity. Game over. Now, time doesn't just warp with speed, it bends with gravity. The closer you are to a massive object, the slower your clock goes. For example, time runs a little slower on the sun than it does on Earth. Even on our own planet, there's a difference. Over the billions of years of the Earth's existence, the core of the Earth is 2.5 years younger than the surface. But the most dramatic effects occur at the most massive objects in the universe, near black holes. Picture this. A cannonball screams into the sky. Gravity grabs it, slows it, yanks it back down. Unless, of course, you fire that sucker at 11 kilometers per second. That's Earth's escape velocity. But try the same with the sun. You're looking at 617 kilometers per second. Light? Light's a whole different beast. It weighs nothing, flies at 300,000 kilometers per second, and slices through space like it owns the place. So, what if there's something out there that even light can't outrun? For centuries, nobody took that seriously, not even Einstein. He scoffed at the idea that a star could collapse beyond all hope. Then came John Wheeler in the 50s, and he gave us a name that would haunt science fiction forever: black hole. Here's how the nightmare unfolds. A star burns bright for billions of years, nuclear fusion battling gravity. But eventually that fire dies. The fusion engine shuts down. And gravity? It wins. The star implodes, shrinks, crushes itself into a singularity. a point of infinite density. Around it forms the event horizon, the ultimate do not cross line. Step past it, you're gone. Light's gone. Everything's gone. Now imagine you jump in. Dramatic? Oh, absolutely. If it's a baby black hole, gravity will shred you limb from limb before you even cross the horizon, your legs getting pulled harder than your head. But if it's a supermassive beast, like the one lurking at the heart of our galaxy, you might not even notice crossing the point of no return. It's silent, smooth, deceptively calm. From the outside, totally different story. To an observer watching you fall, time grinds to a halt. You slow down, redshift, fade out. You never actually cross that line from their point of view, because at the event horizon, time dies. Yeah, inside a black hole, time stops existing. But wait, it gets crazier. In 2023, astronomers stared deep into the past and made a cosmic discovery. Time used to move slower. They tracked quasars, supermassive black holes from 12 billion years ago, surrounded by matter spinning at nearly the speed of light. That chaos glows like fireworks, pulsing with a rhythm. So what did scientists do? They compared those ancient pulses to today's cosmic tempo. Result? Time, back then, ticked 5 times slower. The early universe was in slow motion compared to now. If we travel even further back in time, we see that in the first moments after the Big Bang, time flowed extremely slowly. In a fraction of a second, the universe went through a period of inflation, an incredibly rapid expansion. Processes that would now take millions of years, then happened in a fraction of a second. Imagine a clock being sucked into a black hole. As the clock gets closer to it, it starts to go slower and slower. Time begins to slow down. And now the watch is in the black hole, assuming it can withstand the incredible gravitational force. And what happens? It stops altogether. Not because it's broken, but because time doesn't exist inside the black hole. That's the way it was at the birth of the universe. Stephen Hawking. So here we are, thinking time is some cosmic river that carries us gently from cradle to grave. Time bends, it stretches, it slows to a crawl near a black hole's edge and dances to a different beat across the cosmos. But strip away the poetry. What the hell is time? Einstein cracked the first layer. He smashed the old view and told us time isn't some standalone ticking clock. It's fused with space into a 4-dimensional fabric. Time's just another direction you can warp. But physicist Carlo Rovelli takes it even further. Maybe time doesn't exist at all. Not fundamentally. No ticking, no flow, no now. At the quantum level, Rovelli says, it's just random events. No past, no future, just scattered quantum blips. The flow of time, he writes, is nothing but our inability to see the universe as a whole. We perceive the world like a movie, frame by frame, but the whole film exists all at once. Mind blown. But hang on, if time's not real, how come we remember the past and not the future? Now imagine this. You're watching a movie. The characters feel time flowing. They live it. But you see the whole DVD. You could pause, rewind, jump to the end. The movie feels continuous, but it's just frame. The rest is your brain faking the flow. What if reality works the same way? Back in the 70s, John Wheeler, the same guy who gave us Black Hole, dropped a grenade on physics. Everything is made of bits. Reality isn't made of stuff, it's made of information. Digital, binary, like the universe is running on cosmic code. Sounds nuts, right? Like sci-fi fever dreams after too much coffee and not enough sleep. But here's the kicker. It fits. The Planck time? That's the shortest possible tick of the universe's clock. You can't divide it. Time isn't smooth. It's pixelated. Planck length? Same thing. Try splitting it, doesn't work. That's the universe's minimum resolution. It's built-in pixel grid. Okay, stop for a second and look around you. Everything, this screen, your hands, the chair you're in, looks smooth, solid, continuous. Here's the kicker. It's not really. Reality? Our reality has a minimal unit of time and a minimal unit of space. This is quite reminiscent of a discrete digital system. Now think, what if the speed of light isn't just a speed limit? What if it's the clock rate of the universe's CPU? In a computer, nothing moves faster than the tick of the clock. In this universe, same thing. You want to push something to the limit? Try approaching light speed. time itself slows down because you're maxing out the system's processing power. You're choking the universal processor. Now smash cut to quantum physics. Heisenberg's uncertainty principle? That's just lazy evaluation. The universe doesn't calculate the position and momentum of a particle until you ask for it. That's not philosophy, that's optimization. A trick every good programmer knows. Don't waste resources until you need to. Take the famous experiment with two slits. A particle passes through both slits at once, creating a wave pattern. But when we put a device for observation, the particle passes through only one slit. Isn't this like lazy computing in programming? The system doesn't waste energy on calculations that aren't needed right now. The universe doesn't determine exactly where a particle is until it needs to. Instead, it keeps it as a wave of probabilities in different places at the same time. What if matter is really just a special form of information? After all, both the elementary particle and the bit are the ultimate units of simplicity, one in physics, the other in computer science. Could it be that the laws of nature is simply the most efficient algorithm for compressing data? This isn't New Age rambling. This starts in the 1940s, when the first computers sparked a revolution in thinking. John von Neumann, the guy who literally built the foundation of computing, saw the parallels between thermodynamics and information theory. Edwin James came next, showing how physical systems follow the same logic as code. Then came Konrad Zuse. The man had the guts to say it out loud. The universe is a freaking computer. Space and time, not smooth, discrete, pixelated, like your screen. The concept of a computational universe is still just a hypothesis. Nothing has been proven. However, I am convinced that this idea can help unlock the mysteries of nature. Konrad Zuse. Edward Fredkin didn't just think outside the box, he torched the damn thing. The guy looked at everything, matter, energy, reality, and said, yeah, this is all just information. Not metaphorically, literally. Your body, your phone, a black hole, all just bits in motion. Not atoms, not fields. Binary data. Flip a bit here, flip another there, and boom. Photon, electron, neutron, star. Fredkin saw the universe not as a machine made of stuff, but a machine made of code. No particles, no forces, just configurations of information playing out like a massive cosmic automaton. Everything you've ever seen? Just one of trillions of digital patterns firing across a grid of Planck-sized pixels. And then Jürgen Schmidhuber came in like a mad genius and said, why stop at one universe? According to him, the entire multiverse is just the output of a single short program running on a universal Turing machine, a computer so powerful it can simulate everything, not just our universe, every possible version of it, with every variation of physical laws you can dream of. It's all just code, all of it running from the same brutal, elegant line of logic. Now here's where it gets insane. This idea, digital physics, claims that there's no true randomness, no smooth curves, no infinities. Everything that seems chaotic, it's just computation too complex for our brains. Everything that looks continuous, just pixelated so finely you can't tell the difference. Space, time, even quantum weirdness, all grid work, all rule-driven. This fits right into the wildest ideas in modern physics. Wheeler's it from bit, Tegmark's mathematical multiverse, loop quantum gravity, hidden variables. It's all converging, a digital universe. So what's the problem? We can't test it. We can't see the code. We can't peer into the Planck scale pixels with any telescope or particle collider. All our tools are built for a world we think is continuous. If digital physics is right, then everything we've ever measured is just an approximation of the real code humming underneath. It's like trying to understand a video game by watching the screen and never opening the source code. But if the universe is a program, what's the algorithm? Enter cellular automata, the beating heart of this theory. Imagine a chessboard where where each cell, each square can be either black or white. At each moment of time, the cells change their color according to certain rules, taking into account the state of neighboring cells. The most famous example is Conway's game of life. In the game of life, there is only one simple rule. A cell comes to life if there are 3 living neighbors nearby, survives if there are 2 or 3 living cells, and dies in all other cases. And strangely enough, complex structures are born out of this single rule. For example, the planar is a simple figure of 5 cells that moves diagonally, completely changing shape every 4 generations. The glider gun, on the other hand, is a structure that endlessly producing gliders at regular intervals. And here's the pulsar, a periodic shape that returns to its original state every 3 generations, demonstrating a complex symmetry. There's a sea of everything in the game of life: spaceship, oscillator, hives, and so on. Even a universal computer and von Neumann's self-replicating designs can be built on cellular automata. So here's the big question. If the universe is a cellular automaton, what the hell are the cells? They're not quarks, not photons, they're not even physical. Maybe they're smaller than anything we can ever detect, or maybe they're not things at all. Maybe they're just pure mathematics, code. In 1990, physicist John Wheeler proposed a bold and, for some, crazy idea. Perhaps our entire world is made of information. He called this concept it from bit. Everything in existence, every particle, every force field, even the space-time continuum itself, derives its function, its meaning, and ultimately its very existence from the answers we extract with physical instruments to questions involving yes or no answers. From binary alternatives, from bits, out of bits, symbolizes the idea that every object and event in the physical world has at its core an immaterial source and explanation. What we call reality grows ultimately out of asking yes or no questions and recording the answers to them with apparatus. John Wheeler. John Wheeler wasn't just a physicist. The guy was a mind bender. He loved flipping your brain inside out with simple little games. One of his favorites? 20 questions. You know the drill. Someone thinks of a word and you guess it by firing off yes or no questions. But Wheeler didn't stop there. He threw a wild twist into the game. What if there is no word to begin with? What if the word only forms as you ask the question? Boom. That's not just a party trick. That's a deep crack into the foundation of reality. Wheeler wasn't playing around. He was saying maybe the universe works the exact same way. We think we're uncovering what's already out there, but what if we're actually helping create it? Every observation, every measurement, not passive but participatory. We're not just spectators, we're co-authors of the cosmos. To really drive this home, Wheeler dropped a cosmic bombshell, a thought experiment that'll twist your brain into a Mobius strip. Picture this. Light from a quasar, one of those monstrous objects at the edge of the universe, starts its billion-year journey to Earth. On the way, it cruises past a massive galaxy. That galaxy bends the light, splits it, like a cosmic funhouse mirror, and boom, we see 2 images of the same quasar, hanging in the sky like twin beacons. This isn't fiction, this is real observed science. It's called gravitational lensing. The most famous example? The jaw-dropping Einstein's cross. 4 images of the same quasar staring right back at us. Now here's where it gets freaky. We point our telescopes, we catch those photons, and each photon has to choose a path, left or right, this track or that, like a particle, locked into one route. But if we slap a beam splitter into the mix and turn the setup into an interferometer, the whole game changes. Now the photon's a wave. It doesn't pick a path, it takes every path. And here's the kicker. What the photon does depends on what we choose to do now, today. That photon's been traveling for billions of years, and yet its behavior, wave or particle, is locked in based on a decision we make now. It's not just weird, that's shattering. That's reality snapping under your fingertips. How is this possible? Wheeler saw 3 explanations. 1. Our decision is somehow transmitted back in time to the photons. 2. Our decision and actions were predetermined billions of years ago. 3. The photon has no specific position at all until the moment of measurement. Wheeler chose the 3rd option. While his student Hugh Everett was busy conjuring up infinite parallel worlds, Wheeler went straight for the jugular. Forget worlds, it's all information. This was the birth of his it from bit theory, the idea that everything, from galaxies to gluons, emerges from raw, binary yes-no decisions. Until something gets measured, light doesn't have a position, a momentum, a direction, nothing. Wheeler depicted this idea as a strange loop, with the Big Bang at one end and the eye of the observer at the other. Physics creates observers, and observers participate in the creation of physical reality. Every interaction between particles can be thought of as a question and answer, an elementary act of information processing. Wheeler himself recognized the limitations of this idea at the end of his life. When he calculated the information capacity of the observable universe, he came up with a truly astronomical number, 10 to the 88th power bits. That's not just big, that's mind-breaking. And no, not all the brains, machines, and sensors on Earth, working together till the end of time, could hope to process even a sliver of that. So, no, we don't get to say we are the universe. We're just tuning into a sliver of the signal. As Niels Bohr said, it is wrong to think that the task of physics is to find out what nature is like. Physics is concerned with what we can say about nature. The universe doesn't hand out final answers. It gives you riddles, layered inside puzzles dressed as paradoxes. And in 1983, Wheeler dropped another bomb, the participatory anthropic principle. According to him, we are co-creators of reality as much as any physical objects. Any interaction of particles can be seen as an elementary act of computation, a question and answer. This doesn't mean that reality is made up of bits. It only means that our description of reality is reducible to bits. Observers are necessary for the universe's acquisition of being. The universe does not exist out there independently of us. We inevitably participate in the creation of what we think is happening. We are not mere observers. We are co-creators. In some strange sense, this is a participatory universe. John Wheeler. Wheeler didn't just brush shoulders with madness, he wore it like a badge of honor. Feynman once cracked, "People think Wheeler went nuts at the end of his life. Truth is, he was always nuts. And yet, Wheeler outlived him by 2 decades and never lost a step." His big idea? Pure Pythagoras. Everything is number. But even that old-school math magic runs into a wall. Irrational numbers. Try writing down the square root of 2 in bits. Go ahead, we'll wait. You'll be typing forever. But that didn't stop Wheeler, because this wasn't just about numbers. It was about the machine underneath reality. So why do we keep comparing the universe to a computer? Simple, because it acts like one. A computer is just a data grinder. You throw in some bits, crank the handle, out comes more bits. Every time, the same output for the same input. That's not just calculation. That's the skeleton of function. Some functions are caveman simple. Flip a bit, turn a 0 into a 1. That's the NOT gate. Others, they'll outthink you, outplay you in chess, predict market crashes, write poetry, translate Shakespeare, and describe your selfies in 5 languages. That's AI. And it all rides on one basic truth. Matter can compute. But how? You don't want a rock. It's too stiff. You don't want gas. It's chaos. You need something in between. Something that can flip bits without falling apart. Enter the hero of this whole damn saga. The NAND gate. 2 inputs, 1 output. It spits out a 0 only when both inputs are 1. In all other cases, it screams 1. But chain enough of them together and you've got everything. Add, multiply, run logic, simulate life. From a handful of NANDs, it's the Lego brick of the universe. Stack them right and you can build anything. That's why MIT cooked up a name for it. Computronium. And it turns out the universe is littered with it. Brains? Check. Cellular automata? Check. Turing machines dancing across infinite tapes? Absolutely. Matter isn't just stuff, it's process. It stores, transforms, and remixes information like a cosmic DJ. And maybe, just maybe, that's how life and intelligence even happened. Think about it, the laws of physics are just code. Each formula, an algorithm. They describe how things move, change, interact, like a program running on the hardware of the universe. And just like software, the same function can be written in 1,000 ways. Juan Maldacena blew minds by showing gravity in 5 dimensions is the same as a field theory in 4, 2 different codes. Same damn output. Physicists are just the ultimate hackers trying to crack the source code of everything. But here's the real gut punch. Can everything be reduced to code? What about thoughts, emotions, consciousness? Physicalists say yes, it's all atoms and neurons and circuits firing like logic gates. Your dreams, your heartbreaks, your eureka moments. Just electrons surfing neural networks. And neurons are made up of the same atoms as rocks. You think, therefore your brain computes. Ideas become sounds, sounds become data. It's all digitizable, compressible, transmittable. Physics is the codec of reality. But not everyone buys it. The rebels push back, like Roger Penrose, Nobel legend, who says consciousness isn't just code, it's something deeper, weirder, something quantum. But even if quantum effects play a role in brain function, they are likely just a source of randomness. This doesn't invalidate the computational model of consciousness. It's just that at its core it would be based on quantum algorithms rather than deterministic algorithms. And such consciousness could be modeled on a quantum computer. MIT professor and author of more than 250 scientific papers, Seth Lloyd, in his book Programming the Universe, writes, "As humans, we are just subsystems of the universe with a complexity of about 10 to the 30th degree of bits. There seems to be no theoretical objection to creating an exact replica of a human being, either physically or as a computer simulation. Such an artificial person would perceive a meaningful world, but the experience would be emergent." Feynman wasn't just a genius, he was a fire starter, and one day he asked a question. Why is it that in order to calculate what's happening in a tiny region of space, it takes a computer a huge number of operations? How does nature manage to do these calculations so quickly and efficiently? His answer? We're using the wrong kind of computer. Feynman called it out. We need something new. Something built from the same rules as the universe itself, the quantum computer. Because let's face it, classical computers, no matter how fast, no matter how fancy, are fragile, limited, and stupidly linear. They're bits, just zeros or ones. Flip a coin, get heads or tails. That's it. And they choke if your inputs are even a hair off. But quantum computers, they don't play by those rules. They use qubits, particles that don't just sit at 0 or 1, they sit at both, at once. Think of a coin spinning in the air, forever suspended between heads and tails, and every point in between, that's a qubit, that's superposition. And it gets weirder. Qubits can tangle together in ways that defy logic, entanglement. Change one, and its partner flinches, instantly. Distance doesn't matter, space doesn't matter. It's raw, alien coordination. These machines don't ask direct questions. They whisper to the void. They poke reality without touching it. Weak measurements, counterfactual computation. It's like reading a book without opening the cover, like solving a maze without walking the paths. A quantum computer can also effectively model other quantum systems. As Seth Lloyd puts it, the quantum computer is itself a quantum system, capable of exhibiting a full repertoire of quantum weirdness. Here's the twist in the quantum tale. A quantum computer can do everything a classical one can. 1 qubit? Boom. It can represent 1 bit, no problem. But flip that. Try getting a classical computer to act like a quantum one? Good luck. That's like trying to build a jet engine out of Legos. Why? Because the classical world is just a shadow of the quantum one. Quantum mechanics includes classical mechanics as a special case, like high def including black and white. But the classical world? It can't stretch to cover the quantum realm, not without paying an insane price. Let's break it down. Both classical and quantum computers can simulate stuff, an apple, say, but the quantum machine does it effortlessly. The classical one? It sweats, groans, and eats a supercomputer farm for breakfast. Want to simulate 300 qubits? Better be ready to store 2 to the power of 300 complex numbers. That's more than all the atoms in the entire observable universe. The classical machine flatlines. The quantum one? It lives for this. That's the asymmetry. That's the secret sauce. Quantum modeling is a whole new microscope. It doesn't just zoom in. It rips the veil off nature itself. It shows us how the smallest, weirdest parts of the universe really behave. No more blurry guesses. Now we see. And here's where it gets wild. We're looking at two totally different worldviews. The first says reality is digital, made of clean-cut bits, ones and zeros, switches flipping on and off, nice, neat, mechanical. But the second view, that says reality is quantum all the way down. Everything is made of qubits. Not on or off, but a swirling sea of endless maybes, infinite possibilities. This second idea, everything is qubits. It's not some fringe sci-fi. It's being championed by minds like David Deutsch and Seth Lloyd, and it doesn't replace quantum physics. It reframes it, not as particles and waves, but as pure information processed by the universe itself. Digital physics wants to rebuild quantum theory. It from qubit, it embraces it. It just speaks the truth in the language of information, and in that language, bits. Those zeros and ones are fakes, approximations, oversimplified shadows of something deeper. As Deutsch nailed it, bits and classical computing are approximate properties of qubits that manifest themselves in decoherence. Take an electron, just one. Ask it a question. Hey, which way is your spin pointing? When we measure its spin in one direction, it shows a clear up or down value, but as soon as we try to measure it in the other direction, something strange happens, disappears, and the result becomes completely random. This is not just a technical limitation, it's a fundamental property of nature. According to David Deutsch, a qubit doesn't sit in one state. It lives in all possible states, all at once. When we make it definite in one aspect, it inevitably becomes indefinite in other aspects. It is impossible to create a qubit that is completely the same in all possible dimensions. So the neat, tidy world we think we live in, it's a lie, a projection, a low-res version of reality we get when we zoom out far enough to ignore the weird. But dig deep, look close, and everything starts to blur. Nothing is really yes or no. The true answer is both, and everything in between. Physicist Paula Zitzi pushed the boundary even further. She said space and time themselves, space-time, might be made of qubits. At the smallest possible scale, the fabric of reality is quantum, and when those quantum units interact, they form the ultimate machine, a self-purating, reality-bending quantum computer. And what are the laws of physics in this picture? Just the algorithms this machine runs. That's right. Gravity, electromagnetism, entropy. They're not forces, they're code. But even that might be just step one. Classical information theory turned out to be just a baby version of quantum information theory. So what if qubit theory is also just a piece of a bigger puzzle? What if we're still staring at shadows on the cave wall, thinking we're seeing the full picture? So, is the universe a computer? Hell yes, but not in the sense that we are living in a simulation. The universe is almost certainly not a classical digital computer. Fundamental physical constants cannot be digitized. But the universe can be thought of as a quantum computer that computes in parallel all of its possible states in parallel. This is the deep connection between physics and information theory. The universe is not a simulation. It's a self-calculating quantum system. And in this system, we are all participants, not just observers. What does the universe compute? Answer: itself, its own behavior. As soon as the universe came into being, it immediately began to compute. At first, the constructs it created were simple. They involved elementary particles and established the fundamental laws of physics. Over time, as it processed more and more information, the universe gave rise to increasingly intricate and complex objects, including galaxies, stars, and planets. Life, language, people, society, and culture all owe their existence to the natural ability of matter and energy to process information. The universe's ability to compute explains one of nature's greatest mysteries: how complex systems, like living things, emerge from very simple laws of physics. These laws allow us to predict the future, but only as a probability and only in general terms. The quantum computational nature of the universe is such that the specific details of the future are always unpredictable. They could only be calculated by a computer the size of the universe itself, So, the only way to look into the future is to wait and see what happens. Seth Lloyd. If you enjoyed this video, drop it a like and hit that subscribe button. It only takes a couple of seconds for you, but it gives me a huge wave of motivation to keep making even better content. And don't forget to ring the bell so you never miss a thing.